This is a fairly complex problem involving modification to a Rankine cycle using an open feed water heater. So let's first explain what's going on in the cycle. This is a problem from chapter 9 of the problems module of test. So the state 1 at which the steam enters the turbine is given to us. So in the TS diagram, state 1 is well known. We know two properties. We can find any other properties. And its exit pressure is 7 kPa. As you can see, the condenser is at a pressure of 7 kPa. So this must be, the low pressure line is 7 kPa and the high pressure line is 9 MPa. So a normal cycle will be somewhat like this. However, bleeding from the turbine to the feed water occurs at 0.7 MPa. So at some intermediate pressure, some steam is bled from the turbine. So let's say this is where 0.7 MPa line is. So this would be our state 2. So let's start from scratch again. From state 1, we can see that we know pressure is given to us and temperature is given to us. At state 2, pressure is known. What else is known? Remember, an ideal turbine is isentropic, so S2 must be equals S1. So these are the two properties that are known to us. And then the steam keeps expanding in the turbine, and in the condenser, the pressure, the state is state 3. So at state 3, we know not only the pressure, which is 7 kPa, we also know the entropy as same as state 1. Before you go forward with other states, just one thing to note here, that suppose m dot is the mass flow rate entering the turbine and b dot is the bleeding rate, then the flow that comes to the condenser is m dot minus b dot. So we'll keep that in mind. Okay, let's move forward specifying all the other states. So we are done until state 3. From 3 to 4, we have the condenser where heat is rejected at constant pressure. So state 4, by definition of an ideal cycle, will be saturated. So what can we write about state 4? We know the pressure. P4 is same as P3, which is 7 kPa. And x equals 0 specify saturated liquid state. Now from 4, we use an isentropic pump to raise the pressure. So what should be the pressure at 5? The answer is the pressure at 5 must be equal pressure at 2. Why? Because if pressure in 2 and 5 are not equal, there will be a backflow. Suppose P2 is higher, then the flow will, P2 is higher than P5, then the flow will have will try to turn back this way. So in any mixing system, the pressure of the flows entering must be equal so that they don't create a backflow. So in general, we'll assume that in any mixing chamber, pressure among 2, 5, and 6 are all the same. There is no pressure drop, no friction. Okay, so we know the pressure at state 5. What else do we know? The pump is isentropic. So therefore S5 must be equals S4. So state 5 therefore can be determined. And finally, how do you find out state 6? State 2 and 5 are given, so state 6 can be obtained from the condition that in ideal regeneration cycle, state 6 is saturated liquid. So pressure is the same as P2, which is 7 kPa. Sorry, not 7 kPa, 0.7 MPa. And x equals 0. Well, how do we make sure that at state 6 the quality is 0? In other words, how do you make sure that there is no vapor left here? The answer is that the bleeding rate B dot is controlled so that state 6 is the desired state. As a matter of fact, that is the condition that will allow us to determine B dot as we keep on analyzing this problem. Okay, and finally, from state 6, another pump is used, an isentropic pump, to raise the pressure back to the boiler. So at state 7, we have the boiler inlet condition, which is the pressure must be equals P1, which is 9 MPa. And again, entropy must be equal as 6. So we have defined each state adequately. In other words, there are two properties in each state that are known, so we can find the enthalpies of each state. Now suppose, we'll come back to the details of how to find enthalpies later. But suppose we know the enthalpies of each of the states, because we know two independent properties in each state, so theoretically speaking, we can find enthalpy at each of this given state. So how do we analyze each device? So suppose, let's go one by one. Suppose, what would be the turbine work? Well, notice the turbine doesn't have one inlet and one exit. If we use the energy equation for the turbine, the EDT equals 0. So let's m dot H1 is the energy that enters to the turbine minus m dot, B dot is going out at state 2, and minus m dot minus b dot is the amount that is going out at H3, plus q dot, there is no q dot, minus w dot external, which is w dot turbine, right? So you can see that it turns out to be, if you manipulate this equation, m dot H1 minus H2 plus m dot minus b dot H2 minus H3. And that makes sense. Think about it. The network is from the turbine is m dot is flowing from state 1 to 2, producing this output, and the rest of the turbine handles a flow rate of m dot minus b dot, which is extracted out here. So we don't know what b dot is right now. Okay? So if we know H1, H2, and H3, and somehow if we can figure out what b dot is in relation to m dot, we can find turbine power. Okay, in the condenser, how much heat is rejected? Again, this is a simple one, q dot out. How much flow is coming through the condenser? M dot minus b dot. And the enthalpy goes from H3 minus H4. Okay, now let's go ahead and look at the pump 1, which should be simple. The pump work that goes in here, W dot pump, must be again the flow rate through the pump is m dot minus b dot times H5 minus 4 And the pump 2, so let's call it pump 1, w dot pump 2. Pump 2 handles m dot on the other hand, h7 minus h6. And the boiler, q dot in happens here, m dot h1 minus h7. So we have energy transfer in each device. Now we have derived the formula for each of them. But finally, how do we figure out what B dot should be? And that comes through the energy equation from the open feed water heater. What happens there? The energy that comes in is going out. There is no heat or work transfer. So it's a very simple equation. B dot brings in the energy H2 plus m dot minus B dot brings in the energy H5, and the total mass flow rate at 6 is m dot, and that must be equal m dot H6. So this is the equation that's going to give us a relationship between m dot and B dot. If we know enthalpies, which we should be able to find given everything, given that we know two properties from each state. So therefore, this is going to yield a relationship between m dot and B dot. Okay, this is the time to find out all the enthalpies. Okay, so let's keep on calculating the states now, the enthalpies of each state. State 1, we know pressure, 9 MPa. We know the temperature, and we can use the superheated table to figure out enthalpy, which is 3334, and entropy, which is 6.588. Again, state 2, we know the pressure, and because the entropy is now known, okay, I'll just put double tick to show that we know the values. So if you know the pressure and entropy, we can figure out enthalpy. It's a little more difficult manually solving when you know pressure and entropy. So what we do, we know the pressure, so therefore we can find SF and SG, and we can prove that S2 suppose is bigger than SG, then it's superheated vapor, and therefore we can go to the superheated table, find the pressure table, and then find the entropy that corresponds to 6.588, that row, and from there we figure out what enthalpy is, and it turns out to be 2711. Okay, we carry on like that. So state 3 similarly, actually state 3 also we know pressure and we know entropy, so it's very similar way we figure out enthalpy for state 3 to be 2046. State 4 should be simple because we know the quality. State 4 we know again pressure is known and the quality is 0, saturated liquid. So that gives us enthalpy at state 4 relatively simply as 163. Now a word about finding state 5. State 5 is subcooled liquid or compressed liquid. If you recall, enthalpy at state 5 is enthalpy at U plus P V at state 5, and we know the U and V doesn't depend on temperature, so that is the corresponding value UF at T5 plus P5 VF at T5. That's the compressed liquid model, right? Now T5 and T4 are equal. Why? Because if you recall, in an isentropic situation for liquid, entropy is a function of temperature alone. So if entropy, in an isentropic case, entropy doesn't change, therefore temperature doesn't change. So therefore you can write this as, this can be written as F at 4, which is same as U4 plus P5 V4, which I can write U5 plus, which I can write as U4 plus P4 V4 minus so I add and subtract a term which produces U4 plus PV4 means H4 plus P5 minus P4 times V4. So this is a simplified expression for H5. So to find the liquid enthalpy at 5, we find liquid enthalpy at 4, which you already know, and add this term due to pressure increase. And that can be shown to produce 164. So this is a standard way of finding liquid enthalpy, subcooled liquid enthalpies. State 6 once again is pretty simple because we know is saturated liquid by definition. So P6 is known 0.7 MPa and X equals 0, and that gives us H6 to be 697. Okay, I don't have a value here. Yeah, 697. So we go to the saturation table for 0.7 MPa and pick up the value of HF, that is H6. Again, state 7, which is isentropic state of a liquid, compressed liquid. So just going back to what we have done before, we can use that formula. H7 will be what? H6 plus P7 minus P6 times V at 6. So notice we can pick up V6 from the saturation table, and P7 and P6 are known, and so is H6. Therefore, H7 can be obtained as 706. So we have pretty much obtained enthalpies of every state. So let's now get to the energy analysis. Well, now that we have derived we have evaluated the values of enthalpies of each state, we need to reduce one variable, because right now we still have two mass flow rates, and one of them can be eliminated. How? That's done by an energy balance on the open feed water heater. So as we already wrote the equations before for this, the energy that comes in, okay, let's do it on a fresh page. Energy that comes in, m dot times energy that goes out, m dot times H6 must be equals energy that comes in, b dot times H2, m dot minus b dot times H5. So b dot is extracted from the turbine, and the rest, which is m dot minus b dot, is flowing through this circuit, and they come and mix here, and when they go out, it's again back to m dot. So it should be kind of clear from this diagram. If you manipulate this equation, you will get b dot over m dot. Basically, the fraction that is bled is H6 minus H5 divided by H2 minus H5, which is 0.209. Okay, so based on a flow rate of 1 kg per second, m dot equals 1 kg per second, we can now calculate all the energy transfers in different devices, we can show that the turbine work output, for which we already got an expression in terms of enthalpies, if m dot equals 1, we already know b dot. So instead of rewriting the expression, let me just write down the answers. And you can verify that. We already have the formulas and we have evaluated all the enthalpies. In the condenser, q dot out that is rejected by the condenser is what? Is m dot b dot, m dot minus b dot, h3 minus h4, which is 1488 kilowatt. The turbine, the pumping power in the first pump similarly can be shown to be only 0.54 kilowatt. The second pump consumes 9.2 kilowatt. And finally, the boiler where Q dot in takes place, 2627 kilowatt. Well, in this case, the network then turns out to be okay. Let's do it here. The network is what the turbine produces minus what the pump consumes. And you can show that to be 1140 kilowatt. If you try to find what is Q dot net, that will be Q dot in minus Q dot out, which we know must be equal to 1140, but we good to calculate and show that it'll be 1140. Now, this net output is based on a 1 kg per second flowing through the system. Now, suppose, well, in this particular problem, they mentioned that the net power output is 100 megawatt. So to scale it up, so therefore, the real m dot in the problem should be what? The m dot should be, it can be calculated now, m dot should be 100 megawatt is the net power output divided by, based on 1 kg per second, the net output is only 1140 kilowatt. So if we divide this by 1140 kilowatt, that gives us a mass flow rate of 87.8 kg per second. So if you scale up the whole system, saying that the mass flowing through the boiler is 87.8 kg per second, then we'll produce 100,000 kilowatt, which is 100 megawatt. Also, we can very easily calculate the thermal efficiency of the cycle because we already know the net power. We know what is Q dot in, and that turns out to be 43.37%.